this is an example problem that will connect what we're doing with electrostatics back with some of the work you've done for Physics 1, and that is force diagrams. So as we look at this, this is a problem where we have two balls and it says the mass of these balls is 5 grams, so 0.005 kilograms. The silk thread length here, this length is 50 centimeters, 0.5 meters long, and the balls have the same charge Q, and the threads hang at this angle that's shown. And the question is, what is the magnitude of Q, and what are the signs of the two charges? Well, we know that the two charges have to be the same because they're repelled. So they repel, they're the same charge, but we don't actually have enough information to tell whether they're positive or negative. So that's kind of a tricky question. They're either both positive or both negative. And that's as much as we can say about this. And as you know from doing examples in class, or from knowing Newton's third law, they don't actually have to be the same charge. It's just they said that for this setup, they're given the same charge. And that's the easiest thing to do. You can charge one, let them touch each other, and then they repel like this. Okay, so looking at this, then we can look at the forces. I'm going to draw a force diagram for this rightmost charge, so it looks like this. And we've got tension. I'm going to exaggerate this angle just a little bit. We have tension off in this direction. This angle that we have right here is going to be the 5-degree angle, so this is 5 degrees. And we have, of course, mg that's down, because we have weight that's down and tension, and then the other force, sort of the new force for us here, is that we've got a Coulomb force Coulomb, that's pointing on this object to the right because it's along the line between these two charges, and so it depends on this distance r. So if we like, we can draw this in. This is our force Coulomb. And so what we can recognize, and I guess I should make this to scale, is that this mg is going to equal the y component of the tension, and the Coulomb force is going to equal then the x component of the tension because they're not oscillating. They're just sitting at rest. So if I write my sum of the forces equals mass times acceleration, which is my vector equation, I can write it in both the x and y direction. So I add up all of the forces in the x direction, and there's no acceleration, so those must add to 0. And I can add up all the forces in the y direction, and that equals 0. And since I'm interested in the Coulomb force, the charge, right, I'm trying to find the magnitude of the charge, it makes sense that I would look at what's going on in the x direction and see what I can learn from that. So in the x direction, I have force Coulomb is in the positive direction, minus the force tension in the x is equal to 0. And so as I look at this, the tension force here, tension x, is opposite this 5-degree angle, so I would write that as the total tension sine of 5 degrees, force Coulomb is equal to 0, or my Coulomb force, which would be k, q times q, so q squared, over r, where this is my r distance here, over r squared, is equal to tension sine of 5 degrees. Okay, so what I need is this distance between these two, which I can get from the geometry. K is just my constant that I look up. And if I have my tension, then I can find my charge. So I'm going to use my y equation to find the tension, because in my y equation I have Ty up minus mg is equal to 0. I know the mass. I know m is 0.005 kilograms, so I can find my tension in the y direction, which would allow me to then get my total tension. Because the tension in the y direction is just going to be my tension times then cosine of the angle, because Ty is the adjacent to this 5-degree angle here, that where the tension is the hypotenuse. So tension times cosine of 5 degrees is equal to mg, or the tension is equal to mg over cosine of 5 degrees. Okay, so I can plug that in and put that right into here, and I get k q squared over r squared is equal to mg sine of 5 divided by cosine, so that we would call tangent of 5 degrees. And when I calculate that out by putting in 0.005 kilograms, 9.8 meters per second squared, this altogether gives me 0.0043 newtons, just to give us a number in there. Okay, now to find this radius, this distance between these two objects, what I'm going to do is sort of redraw this, a little exaggerated, of course. So this is 0.5 meters. This is 5 degrees, and so it's pretty straightforward to get this distance x, which would be half of the radius. So in fact, we can see that x is on the sine. We can say sine of 5 degrees is equal to x over 0.5 meters, or x is equal to, I get 0.0436 meters, or my r is about 0.087 meters. And that gives me all of my pieces, because if I put this in here, k is approximately 9 times 10 to the 9th, right, 8.99, but 9 works just fine for this. Newtons, meters squared per coulomb squared, so that units work out. Then I can plug all of these things in, and I have 9 times 10 to the 9th Newton meters squared per coulomb squared times q squared. My r is 0.087 meters squared is equal to 0.0043 newtons. The newtons cancel out, the meters squared cancels there, and so my q is equal to 6 times 10 to the minus 8 coulombs. Okay, so that is the charge on each of these. So that's the charge that's on this. This is 6 times 10 to the minus 8 coulombs. This is also 6 times 10 to the minus 8 coulombs. So that's the charge on these little masses, and that's what provides the 5 degrees.